Thank you very much. Thank you, the conference organizers. It's great to be here. Thank you to the session chairs. My name is Onur Tigli, and I'm here to present our paper that we've been working on for a while with a senior student in my lab, Senveli, Sukru Senveli, and he couldn't be here, so I'm here. This is my attempt to present the work that we've been doing. So I'll try to give you a background, and we have been working on this surface acoustic wave devices for a while now, including back in my postdoc and as a faculty, but this work had been a collection of works over the course of a decade or so, and this is sort of the pinnacle that we reached recently. And I'm going to give you some current research studies, the devices, the FEM analysis, experiments, and I'll conclude with some results. So why are we working in this field? I'm a faculty with both engineering and medical school and pathology department specific, and I'm interested in cancer diagnosis specifically, and I've been doing biosensing work. And one idea that when you talk to medical personnel is that they're interested in is microparticle analysis. And for this case, microanalysis gives a great promise for biological cells, bacteria, viruses, and people are very much interested in their properties at that micron scale. And why do we do it? Because it's economical, small sample volumes. We are able to design these things in MEM scale. And also, we are really interested in looking at individual phenomena like rare events, heterogeneous population of cells, trying to distinguish, separate, or analyze these cells in specific. So the work that we have been doing in surface acoustic waves started back when I was at GW. 30 to 500 megahertz ultrasound waves on surfaces. As most of us probably know, piezoelectric crystals are used in these type of devices. We are mostly interested, and most of the devices we produce are interested in Rayleigh waves, and they offer sagittal displacements and surface mass loading sensitivity is increased. When we started this work, we were interested in mass loading, classic mass loading type of devices. But what we encountered was there's a major problem in soil literature, and also we also encountered this problem, and that's the liquid coupling. And liquids cause damping, and this damping causes your sensor outputs to not give you the best results, specifically when you're dealing with microfluidics. So we looked into different types of devices, but this is a typical SAW device, as you know, input IDT, output IDT. Surface acoustic waves are delivered between the two, and anything you have biochemical coating on the surface is going to be sensitive to your analyze. Now, you typically get is the pointer here? Okay. You typically get an insertion loss as given over here, and a phase response, just like that if you have a perfect filter operation. And this is a typical device that we have around 197 megahertz operating. So in our previous work recently published in Journal of Applied Physics, we looked at liquid coupling with Rayleigh waves. So our initial original idea was to have microcavities on the path of the wave. Instead of the original mass loading scheme, we are trying to use cavities that the wave is going to interact directly with the liquid itself. So we are working at 200 megahertz frequency band, and the cavities that I'm going to show you in a second, roughly the volumes are range between 10 picoliters and 15 picoliters, but we are trying to go below 10 picoliters. And the liquid work that we did was a combination of glycerin and water, and it's going to come clear in a second why glycerin. And the substrate that we have been using are quartz and lithium niobate, which are pretty common in surface acoustic wave field. So our model was to have, again, instead of having the liquid covering the surface, have a microcavity where liquid is in directly interaction between the surface acoustic wave, because we know that it's going to travel in transverse direction. And we have air over here, liquid, and the substrate. And if you look at the varying different viscosities, we saw that we are able to distinguish in a very nice manner the viscosity differential, and depending on the sound velocity, they have linear correlation between the two. So in this previous work, what we did was, both with lithium niobate and quartz, we analyzed and looked at three major components, which are pretty common, again, in solid devices: absolute frequency shift, phase difference, and insertion loss. And what we came to conclude from our work, published work at Sensors and Actuators, was that mostly the phase difference started to give us monotonic response, which is much better than the insertion loss and the absolute frequency shift. So we found that phase difference is going to be much reliable in analyzing liquids. Then our work started to look at, like I said, we're interested in biological applications, so liquids are not just sufficient. We are also interested in embedding some sort of solid or solid-like structures into this idea. So we built these new generation of sensors using ST quartz and passband frequency of 197 megahertz with cavities of 16 to 24 micrometers and 16 to 32 micrometers. We are looking at two different types, circular and rectangular. So we are trying to also analyze the effect of that shape of the cavities in the interaction. And also, we are using, for the test that I'm going to present over here, we're using polystyrene microbeads in liquid. And our liquid formation is based on the previous work, the liquid work that I showed you, 90% glycerin. So these are our devices. As you can see, that's the sensing cavity within the path, and we're trying to look at the interaction. So the question that most interested us was that how is the liquid going to act, and how is the solid going to act when they actually interact with the waves at these frequencies? So when you look at it with the viscoelasticity models, we did for pure glycerin up till pure water with increasing percentages of glycerin. And 90% glycerin, which is what we are using in our test, showed Newtonian liquid-like behavior at 200 megahertz or so, with a correction factor of 97%, which adds a little bit of a shift. But it is still reliable up over here, if you can see. So we picked that, and also this was embedded in our FEM model with the glycerin water mixture as our Newtonian liquid over here. Polystyrene is acting like standard linear elastic, and we have the ST quartz model we developed. So our model has unit to metallization ratio, 64 electrode pairs, 16 micrometer wavelength, and with an aperture of 1.5 lambdas. And we used, as in most of the SOA models, one of the concerns is the absorbance of the surrounding material, and this is still a concern in real life experimentation. But we used perfectly matched layers to eliminate any reflections that will also contribute into the phase output. So we are trying to eliminate that by using PMLs. Perfectly matched model, and then we were able to get a really good SOA response around 197, 200 megahertz range for the quartz. And let's see, and this is our model. I'm going to show you how the interaction occurs. Input IDTs are here, 3D model. The microbead is embedded with the liquid surrounding and the output electrodes. And here we go. If you can see, I'm not sure whether the projector has good resolution, but you can see the propagation of the wave, interaction with the microbead, and then at the output, the delayed response as it comes out. And if you look at it at a cross section, I'm going to show you in a second, you're going to see the transverse wave traveling and then coming out with a phase delay at the output. So here we go. I think they're playing fine now. So we have incremental phase shifts for 50 micrometer diameter here, 20 micrometer diameter. You're looking at pressure in liquid region of these maps over here, and displacement in other regions, so including the microbead. So this is how the wave travels, surrounding it, getting into the liquid, creating a resonance cavity, and then interacting with the bead, then passing on both in transverse mode, and then coming out at the other end, and we are measuring the phase shift. And if you look at our results, and these are simulation again, I'm going to show you the experimental in a second, the absolute phase difference, we were able to get between 10, 15, and 20 micrometer beads, which is what we set up our tests with. Briefly on the device fabrication real quick, We do a classic acetone cleaning, and then in our quartz substrate, then we do photoresist spinning, exposure and development, wet etching of the hard mask. We need the hard mask to open up the cavities so that it doesn't impact the quartz underneath. Then we remove the hard mask, negative photoresist spinning, exposure and development, and E-beam evaporation, then a lift-off process so that we have the metal IDTs. And this is how the device is obtained. So this is what it looks like. A typical SAW IDT, these are 100 micron scale bar over here. We have obviously GSG or, in this case, this is GSG probing. So we are working around 200 megahertz. We need RF probing. Over here, you see those, and you see the cavity. The depth of the cavity is roughly around, in this case, I believe this is a tilted image, I think 8 to 10 microns over here. And cavity size and a typical microbead, this is less than, mind you that we are just doing these tests and trying to take the SCMs. We need to get rid of the liquid, obviously, other than if you want to use environmental conditions. Okay. One major challenge that we run into was in terms of depositing and dispensation of these microbeads. It's even harder with microbeads and liquid. It was hard with liquids, and it's even harder with the microbeads and the liquids. So this is a huge dispensation challenge, but we came up with an interesting idea when we were working with Chen in the lab, and we thought that why can't we use just typical DC tungsten probes to actually manipulate these liquids in the microbead condition. And this is exactly what we are doing. We are using glycerin, allows us to have surface tension enough and an angle of 40 degrees or so, so that we can actually move things around just like that and place the bead, let the liquid sit in there. And we are still running into the, okay, let's see if this is going to work. I'm going to show you these videos. No, I need to get out here for a second. Bear with me. Okay. Let's see if this works. Okay, what we are doing over here is picking up the liquid that is covered glycerin water combination with the bead and moving the bead around. And we were really successful in getting this in a very high precision. Still, it's manual, and we want to get high throughput. But I also want to show you this that actually shows the device formation. As you can see, let me play that for another time. And the bead is placed, and then we can remove the liquid, and the cavity is filled. But one might ask the question, and that actually comes into play later on when we do the actual experiments, is that the bead, in this case, is a rectangular cavity. The bead is perfectly located, but it's not centered. So as the size of the bead increases, we start to get less and less error. As the size is getting smaller, we're getting higher errors because we are not we don't have high precision in terms of placement of the bead. But that's all accounted in our models as well. So, slide. So this is our setup. You have your RF network analyzer, typical. We are monitoring the movements and everything here. These are our positioners for micromanipulation of the liquid and the beads, and the probe station measurements are directly taken from this test setup. So 4 measurements each in results 10, 15, and 20 microns. As I said, relatively high error rate, inaccuracy rather, larger relative error for smaller beads versus higher beads, but we get a really nice increase and direct response in terms of absolute phase shift. So in conclusion, sensing size of particles was achieved with varying different sizes for solids in liquids. So we have already presented in 2 separate publications the liquid formation as well. And less than sample size of 10 picoliters, which promises great biological applications for us. Actually, we're currently working on interesting cancer-related applications. Output phase measurement sensitivity, roughly around 0.14, 0.81, 3.54 for 10, 15, and 20 micron beads. And it has, like I said, very interesting applications we are looking forward to. This is Sukru from Senveli, who had been working on this with me for a while now, so he couldn't be here. But he wishes that he was here. It's a great place to be. That's me. That's the team. Although we recently lost LeBron James, we are still basketball fans in Miami, so we go and watch games. And this is our website. Feel free to visit and get more information. I'll just like to thank our sponsors, specifically National Science Foundation, for the funding for this work. With that, I'll conclude. 2 seconds.